Hi. In the last video, I worked on polishing up the control ROM control circuitry and creating a schematic for that. Today, I want to get into the actual control ROMs themselves. I got a little bit of work to do to finish off the emulator for that, but I should be able to very quickly turn around and get a schematic pulled together and hopefully get that all on Breadboard. Let's see what we can do today. Here we go.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
Okay, let's jump right in. The first order of business is to create a 74 HC, LS, whatever your logic family is, 164 IC, and put that into the emulator and get that emulating. That way we can assemble all the components we need in order to put together a ROM module. Okay, I'm not going to spend too much time with this. It looks very similar to most of the rest of the ICs that I've done. The updates to the A and B input pins are very trivial. They don't actually trigger anything until you have the rising edge of the clock. So they can change and update as necessary. There's nothing downstream that takes place from that. Clear and clock, on the other hand, need to be managed a little bit more tightly. So let's go through that a little bit. On a clear, if the actual, so I update the pin value, and then only if the state is low do I actually need to do anything. It's an active low signal. So if the pin value is high, then I just go ahead and return. There's nothing else to do. And then here I'm taking very good care to make sure that I don't update a pin that actually doesn't change in value. So if the pin's already low, there's nothing really more to do. If it isn't low, then I update it to be low and go ahead and emit the change that that pin has changed. And I do that 8 times. The clock is similar. I've got some sanity checks up front. If my clear pin is low, the clock is irrelevant, so I do absolutely nothing. I could probably change the state of the clock, so I'll go ahead and move that because I think that's going to end up proving to be a bug. If my new state is the same as my existing state, then there's nothing else to do here either. It's basically an update when nothing has updated. So now if my state is actually a high to low transition, the only thing that's left are transitions. There's nothing to do there because nothing's actually going to change. It's only on a low to high transition that things get latched. And so here again, I'm careful to make sure that only when the value of the pin, output pin, has changed do I actually perform an update and signal that something has changed. So I'm checking the new value against the current value, and if they are different, then I go ahead and perform the update and emit that things have changed. And I do that 7 times. The 8th time really is just an AND of the A and B pins, and if both of them are high, then the new A output value is high, otherwise it's low. So I pre-calculate what the new A value is going to be, and if it changes the value of the output A, then I update it and signal that it has changed. Now I haven't tested this yet, and in order to test this, I need to build out an actual EEPROM control module that has the serial EEPROM and the SRAM and the shift register on it, and make sure that I get the signal in and signal out correct. So let me start pulling that together. I've got some stuff that's stuffed into the build now, but it's not actually aggregated into a module that I could turn into a PCB. So maybe a little bit of work on that. We'll come back and review those changes. Well, I got down to this point in the wire up code and realized I made a pretty crucial rookie mistake. Now, there were a couple of other mistakes that I have made up until this point, but this one was rather egregious to the point that I need to stop and take a step back and relook at my design. So the challenge here is these signals and these signals all need to come from the control module, because they would be duplicated for each control ROM, and I don't want to shape those on the control ROM themselves. But more importantly, this 74HC164 is putting data on an 8-bit data bus where this RAM will eventually also put data onto an 8-bit data bus. And I have nothing to separate this data from this data. Now, I had intended to latch and pass off this 8-bit data from the RAM off to other modules and demultiplexers and the like. But I also need to insert in here a line driver such that the data coming off the 164, once it's done shifting and loading and doing all of that stuff, that data is no longer pushed out onto that 8-bit data bus going off this module. So this is going to change this setup just a little bit. Now I'm going to continue to move forward with the ROM. I'm going to circle back to the control module, and then I still hope to, after doing all of that work, at least get a breadboard out. Okay, so with those changes to the block diagram, let me get back into the code and make sure that I have everything shored up properly. Okay, I'm close here, but I do still have a problem to solve. Let me explain what I've done so far. So I have gone ahead and completed the wire up, in quotes because it's all code, for the control ROM. Now there are several components of this which are copied out. I'll get to that here in a second. Before I do, I also created an 8-bit bus, which is a copy of and then stripped down version of the 16-bit bus. And I will likely end up doing the same and creating a 1-bit bus. I'm going to need something similar to that for the reset hold, but that's not quite for this video yet. All right, here in the control ROM, I have the comment here, be careful of infinite recursion. Pins are bidirectional. And that's for, in real life, they're bidirectional. They can read and write. Basically, it's a bidirectional transceiver that's built into the end of this RAM. And you can see I've got one of those connections commented out. If I run it in this state, it does run. I'm not actually copying anything, but it's at least executing, and that's really the point at this point. I haven't gotten into the details of the debug. Now, if I uncomment this, rebuild, and rerun, I end up with a segmentation fault. Ultimately, what's happening is that infinite recursion that I was speaking about. So it is bouncing back and forth, being updated and then turning around and updating, and then being updated and then turning around and updating. And my flaw is actually in the implementation of my SRAM. And I have not really taken the bidirectional nature of those pins into account. So I have just the pins in a simplistic state, but it really needs to be what is asserting, and is it asserting or is it consuming? And so let me then turn around and get that all settled. I'm going to have to re-implement my SRAM module, and then I can work on what do I need to do in order to get the control ROM itself debugged. Okay, and with those changes made, it is now running. And as expected, I actually had to add a little bit of state to the SRAM to indicate whether or not it was outputting a value out onto the bus, and if it was, what value that was. That value cannot be stored in the pins as I had originally had that set. So I'm now storing it within the IC itself as a state piece, and now I'm just discerning whether or not I should be outputting. And if so, I take the value that should be outputting and put that out onto the signals itself. So down here, my new Q output is calculated up here. And then if there's a change in bit, I emit that signal, but I do not touch the pins in this case. All right, now I've got to get back to this and do some debugging and find out why that's not actually doing anything. I'll come back when I know something more definitive. Okay, this moment right here. This is the reason I decided to go into the emulator first rather than straight into hardware, is anticipation for this moment or something like it. What am I talking about? Well, I do have the emulator working, and if you watch up here, I am getting shifts happening across, so that's all good. But in my debug output, if you look at what's going on here, my very first write is to address 7FFD. Now that is the address that we reload into the address ROM. It has a value of 0, which is fine. This value 0 is kind of the startup value. Then 7FFE happens, then 7FFF happens. Address 0 is supposed to be a byte 0. So if you notice up here in the start, I've got 8 bits that count through, but the address itself doesn't change. Okay, so I've got something to address there as well. And I can brute force this change. I can advance this by 1. I'd likely end up probably being okay at the end, but I'm not absolutely certain. My bigger concern is this address 0, which could be address 1, is 9, and that's in hexadecimal, by the way. But if I go to hex edit and look at the actual ROM, it should be hex 13. All right, so you're getting totally wrong values. Not totally wrong. They're close, but they're not totally wrong. Okay, so I've got up on the screen here a representation of what this should look like. Now I am expecting 0, 1, 3, 1, 3, and 0. What I'm getting is this first byte is offset. My 0 bit or 0 byte is 9, then I'm getting 8, 9, and then 8, 0. So just in case it's not clear what's going on, let me remove the spaces and just chain these bits together. Do you see it yet? What happens if I do this? Can you see it now? I'm off by 1 bit. And so what this tells me, and it's one of the things that I had mentioned earlier in a previous video, I'm either guaranteed to be successful or guaranteed to fail. And one of the things that I've got going on here is a race condition with the clock. There are things that need the clock at the same time, and the clocks themselves are basically evenly matched, but the temperature of an IC, the length of a trace, whatever is going to dictate what wins. So if you're not familiar with a race condition, consider 2 evenly matched runners doing a 100-yard dash. Whichever one gets off the line fastest is going to be the winner. It's not a matter of speed because they're evenly matched. All right, so what to do about this? Well, I do have to take a step back. I have to go back to the actual block level diagram and revisit that and figure out what the heck to do about this. In the back of my head right now, I am considering adding an extra step in the bits counter so that it counts down 9 bits instead of 8. And that 9th bit will be used to control the latching. And what that would do then is it would take the race condition totally out of play, assuming that I implemented it correctly. But here I am, I'm probably about 12 minutes into a video, and I'm gonna have to take a step back and revisit my thinking. So it'll be just a few minutes for you, but it's likely gonna be a few days for me as I try to figure out exactly how to handle this. So stay tuned. Okay, let's start with a quick cleanup of some of the signals that I've had to change as part of my debugging. Now, this is not the point of this segment. I really do want to try to create something that's a little bit more deterministic. And that's going to rely on the behavior of the counter ICs. So let's pull those out onto their own block diagram. And we'll talk real quick about the current behavior now. And this is incorrect, and it does have race conditions that are built into there. And as I go through this, I realized that I was far too heavily dependent on the borrow out flag coming off the bits counter. All right, so there's 9 states that are gone through in order to count 8 bits. 8 and 0 are shared. They form a complete clock cycle themselves. So the counter is loaded with the value 8 on the first, and that's the low cycle of the clock. On the first increment of the clock after that, 1 bit is shifted, and that's bit counter 7, so it's decremented at that point as well. Next one down is shift bit 2. Next one down is shift bit 3, 4, 5, 6, 7. When I get to 8, only half of that 8 is visible at counter 0, and that's the high half of the clock. On the falling edge of the clock, the value is actually loaded, and we're back up to the value of 8. Okay, so that doesn't work. What would happen if I increase the load value on the bits counter to 9 changing the number of states to 10, both the first and the last still being a half of a clock cycle each, where that first state is the load value, the 8 bits get loaded in each individual state from there, and the last state then controls the latch. Well, that seemed reasonable. I first started considering this in terms of counting and shifting versus latching, where if any one of the bits of the bit counter IC was 1, then I was counting and shifting. Otherwise, if they were all 0, then I would be latching. And so my behaviors with the other ICs ended up looking like this, where the count signal, as I've got it called here, would be ANDed with the clock. Well, with that, I've just moved the monkey. I've still got a race condition. I just traded one bad race condition for another. That isn't going to work. So rather than taking that count signal, which was dependent on the decrement of the counter down to 0, which was dependent on the clock, ANDing that with the clock itself, so I've got two clocks racing with each other. So the real solution here became back that drop to low on that count cycle back up half of a clock tick, so that it took that clock for the decrement down to 0 totally out of play. If I could reset a set reset latch that half clock cycle early and then set it just as the borrow out would go high, what that would give me is a full clock cycle properly distributed and take that clock totally out of play. No race condition. And I can hear you asking me, but Adam, isn't that extra clock cycle going to kill performance? Yeah, it will for loading the SRAM from the EEPROM. It's going to add about 13% to the time that I was seeing before. 12.5 if you want to be accurate. But I'm willing to trade performance for stability. The last thing I want to do is get into a situation on the breadboards again, or on PCB for that matter, where I am chasing some kind of a timing problem. Okay, so with that, let's update the main block diagram. I need another set reset latch, which will have an output we call QS. The clock on the EEPROM, the clock on the 74HC164, the clock on the 74HC165 all need to be updated. My SRAM output enable remains the same, but the write enable and chip enable gets simplified, plus the address increment gets changed from the borrow out bit to the QS signal. With that, I'm going to print this. I'm going to have a good stare at it and make sure that I'm not missing something. Okay, I'm going to need a little bit of room here, so let me slide this shifting SR latch over. I had a pretty good think on this last night, and it's actually the next day here for me. There's several optimizations that can be done here that are relatively easy to identify, and one problem. So let me see if I can outline what I've got going on here. We'll start with a simple gate count. Now, when I do this, if a signal is natively available, such as in an SR latch or a D-type latch, where both the output or result and its inverted result are outputted, then I'm not going to count that as a gate. But if I have to manually take care of any of these signals in order to get them shaped properly for my needs, then obviously I need to count that as a gate. So my simple gate count looks like this. 5 NAND gates, 2 for this SR latch, 2 for this SR latch, and one more here. Now that requires 2 ICs, that's the number in parentheses. I need 14 AND gates, 2 here, 2 here, 2 here, 1 here, 3 here, and 4 here. 1 OR gate up here, and 7 inverters. 4 here, 2 here, and 1 sneaky one up here. One of the most obvious optimizations are these 3 clock signals here. They're all exactly the same signal, so I can build it once and use it 3 times. That saves me 4 AND gates. Next up down here in the corner, both bits output C and bits output B are inverted in these 2 signals here. So I can invert them once and use them twice. That saves me 2 inverters, but there's still low-hanging fruit over here in the corner. Bits C inverted and bits B inverted and bits A are used in both signals. So I can combine those together, use them twice, and save 2 more AND gates. Okay, one more optimization which may or may not be so obvious is this chip select signal here, which uses a NAND gate, can be rewritten in equivalent logic to be not QC or QR. And by doing that, that saves me a NAND gate, saving me an IC, and increases my usage for the OR gates by 1. And now for the problem I missed last night. Have you noticed it yet? Well, in the shifting SR latch, I have positive logic going into it, but set and reset are active low signals. So I need to invert that entire logic sequence combination. That adds 2 more inverters and adds another IC back. Okay, so that's the new plan. Let me get my head down, get into the code, and I will shore up the control ROM control module, and then we'll come back and give this a test and see how this works. Okay, well, I'd like to say it was close, but it took me a little bit to get this running. It was largely a gut and replace of the existing code, but I do have it running. There were some changes that I did need to make, and it's not quite running perfectly. So let me show you what the problem is before I show you the changes I had to make to get it to run this far. If you look down here in the corner, every time the address changes, you can see I'm sweeping across several addresses as the individual bits change. And I had intended that to commit the write to an address before the address itself changed. So this is just another race condition that I've got, and really what I need to do is I now need to back up the rising edge of my shifting a half of a clock tick. All right, let me show you the changes I had to make first. Well, so I guess it turns out that when I'm looking at active low signals, for whatever reason, when I'm programming, I'm still pushing towards active high things. I guess I'm going to have to get my head around that a little bit. Okay, the first change I had to make was for the shifting clock, be that for the 164, the 165, or the serial EEPROM. I needed to take the inverted shifting latch. And the reason I had to do that is in the beginning I started saying that I was going to set that signal high while I was not shifting and low when I was shifting. And that logic did not match the definition that I was putting in. And so I ended up changing that midstream and didn't change everything appropriately, certainly not my thinking. The second change I had to make was on chip enable because I had that shifting output on that SR latch wrong. I had to invert that. But I also had to invert the entire sequence. The inverse of not QS or not QC is really an AND gate, but I don't have a spare AND gate. But I do have spare OR and spare inverter gates. And so I went with that implementation. Now, my problem with latching the correct value really comes back to this slide, and specifically these 2 tables. So let me isolate those. In the top table, where I proposed my deterministic logic, I said I was going to latch while the counter value was 0. So what I really need is I need that SRAM write enable to go low on the low clock cycle of 1 and return high when that bit counter value goes to 0, a half of a clock step before the address is incremented. So now to do that, I have my QS reset signal, which will actually fulfill that. That said, I can leverage that to be my write enable signal. Let me make that change in code. But once again, I have traded one race condition for another. So what am I doing wrong here? Well, if you look at the SRAM write enable signal, it has both the counter bits and the clock in the same logic evaluation. And there's a delay between when the clock goes high for incrementing or decrementing the counter IC, and when that new count is presented out onto the pins. And you're going to say, but Adam, it works just fine with that QS set reset latch. Yeah, it does. And the reason is because that's actually debalanced. It doesn't matter if the signal for set or reset, for that matter, goes high, low, however many times, as long as the opposite signal doesn't transition during that time. And what happens is I end up with a debalanced situation where as soon as the first time that signal goes low, it stays low until the opposite signal sends my output back high again. All right, so let's try to do something here. I can use that signal to set a latch, set reset latch, and then a different signal, which would be all four of those output pins going low, to then set that latch. And the reason I want to do that way is if I reset it on that same signal and then set it, then I've got a high going transition, which will take care of the latching of that SRAM for me. Let's give that a shot. Okay, and here you go. You'll notice that I'm only getting one value latched at each address. Now, I will admit that the value being latched is incorrect, and I now need to go investigate that in the shift register, but the SRAM itself is actually operating properly. More debugging. This actually took a little bit of effort to debug, but I do think I have it. You can see here that it is going through the process of copying the EEPROM to SRAM. I added the QL signal, which is for latching, and I have on the screen in the background the fact that it has reset, meaning I do have a problem with my reset and how it was actually dealing with reset. And the problem is the control ROM control module would initialize and start counting before the control ROM 0 was ever actually constructed. And so it threw things out of sync. And that ultimately ended up being the problem. So I had to build custom circuitry to hold everything actually in reset properly until I was ready to let it go. There's more to do on that, and I have an issue logged out on GitHub for that, and that will get wrapped up here shortly, not in this video. In the meantime, I do believe that this is going to make the actual hardware more stable. Could I have gotten away with not adding the extra clock cycle? Yeah, probably. I don't know for sure. But certainly this is far more deterministic. Yeah, it's a lot more complicated as well. But it is now far more deterministic as to what the results are going to be. And I don't have to rely on a race condition and one certain IC winning out over another IC. This should hopefully allow this to run at the speed of the counter ICs that are generating the address. So as fast as I can get those to go is my speed limit here. But finally, as this is wrapping up, I do a comparison between the EEPROM and what is loaded in the SRAM. I do that in the software just to make sure that everything got copied over properly. I'm also setting the SRAM to be hex FF before I start copying. That then gives me the ability to make sure that everything actually gets copied, because anything that is unused right now in the EEPROM is forced to be 0 when I create the control logic ROM binary file. And this looks perfect. Well, I got a new camera since the intro and this wrap-up segment. I'm not quite sure I like it, so we'll see how that ends up turning out. I was really ambitious in the beginning and thought I'd actually be able to get to the point of updating the schematic and putting at least something on Breadboard. And unfortunately, I was not able to get that far. There was a lot to go back and rethink that I wasn't quite taking into account. Again, it's a good reason for doing this in an emulator first to make sure that I identify all the problems I'm going to run into. But I feel very confident at this point, turning around and committing this to schematic and committing this to Breadboard. That's going to be the focus of the next video. I'm anxious to get there. I know several of you are too. We'll see you soon.